Good morning, everyone. Since I can't thank the organizers for inviting me, I won't. The title of my talk today is Flux Periodicity in Higher Order Topological Superconductors. This is actually work in progress with Sumanjyoti De, who is a student at HRI, and Udit Khanna, who is a former student and is now a postdoc at Tel Aviv University and Weizmann Institute. I thought I'll give the talk anyway because we get feedback on what we really we started out doing. So the plan of the talk is to give a very brief introduction to higher order topological insulators and superconductors. Then I'll give a brief idea of what one, at least for the students, of what one means by this flux periodicity of superconducting rings. And then I'll discuss our work and results. So Deeptiman has already given an introduction to topological insulators, but I'll just briefly say what they are. They're insulators which have some property to which an integer can be assigned, which depends only on global properties and cannot be destroyed by impurities or disorder. That's what one means by saying that they have topological protection. And at the boundaries between different topological phases, one can have gapless edge, or depending on the dimension, surface states. And the standard picture for topological insulators, as you already told you, was to have a gapped d-dimensional bulk and gapless d-1 dimensional edge states. The simplest example that everybody knows, or many, which is well known, is the Su-Schrieffer-Heeger model in one dimension, where you have two different hoppings for between neighboring sites. And I'm not going to go into this. I just wanted to say that this has two distinct phases, one of which has edge states. And here edge states are basically zero-dimensional modes. Because this is a one-dimensional model, you would expect the edge states to be zero-dimensional quantum mechanical modes. And that's what I wanted to say. They will have d-1, which is 1 minus 1 is zero-dimensional states. The other thing is what we've been talking about in this conference all the time, the quantum Hall effect and quantum spin Hall effect in 2 dimensions, where d is 2, and you have d-1 or one-dimensional edge states. And then you can also have topological insulators in 3 dimensions, where that means d is 3, which means that the edge or surface states there are 2-dimensional. And so the bulk is gapped, and you have gapless surface states. The distinction in this new higher order topological insulators is that d-dimensional gapped bulk states will have d minus n, where n can be some number, and that will give you the nth order topological insulator. So the usual topological insulators that one have are now called first order topological insulators. You can have second order and presumably third order and higher. So the examples are 2-dimensional lattices with zero-dimensional gapless corner states, because here you have a 2-dimensional bulk, but the edge states are also gapped, and it's only the states at the zero-dimensional states at the 4 corners which are gapless. And you can have 3-dimensional lattices. I can't hear. Yeah, that will come across.
What is the difference between the blue and the red corners?
Meaning they're positive and negative charged in the sense of the topological charge that they have, the corner charges. And these come about because essentially it's a quadrupolar insulator. I think he was going to talk much more, Adip is going to talk much more about it, that it's just that the normal topological insulators come by quantizing the dipole moment. Higher order topological insulators come by quantizing the quadrupole moment. And Adip is going to talk about that. It's not that needed for this talk. I just wanted to hear, I'm introducing them. And these are, you can also have 3-dimensional lattices with hinge states. As you can see, these also go in opposite directions, in the different directions. Here the surfaces are gapped, the 3 dimensions are gapped, and only the states which are localized on the hinges are gapless. So the idea is that even if the band structure of the material appears to be topologically trivial at first order, it can still have non-trivial topology. In some sense, you can think of it as a bulk being gapped, and the edge states themselves are also gapped, but they are topological, so they can have edge states. So as Diptiman already said, these are like a boundary of a boundary. And these need crystalline symmetries in the bulk to exist, otherwise they don't exist. And I just wanted to mention, though I don't know much about it, that there's a recent claim that bismuth is a higher order topological insulator. And it's not the surface of the crystal, but the hinges that host topologically protecting conducting states. So with this, I want to now generalize to higher order topological superconductors. So what one wants to say that the corner states that Diptiman was talking about will now generalize to Majorana modes at the corners of two-dimensional topological superconductors. If you had three-dimensional superconductors, you'll have chiral hinge Majorana modes at the edges of them. And what I'm going to do over here is basically start with, since not everybody may be familiar with topological superconductors and Majorana modes at the edge of the topological superconductor, I will start with the toy model, which is the Hamiltonian in 1D. Okay, what I wanted to say here is just simply that for the two-dimensional Majorana mode, for this higher order topological superconductors also, there exists a toy model which is analogous to what is written for the toy model or the Kitaev model written in terms of Majoranas. Since this itself may not be familiar to everybody, what I'll do is first discuss the usual topological superconductors and give a very brief introduction to the usual topological superconductors and Majorana modes, and then we'll go on to the corner modes in a two-dimensional higher order topological superconductor. So the simplest case here is to study a toy model which was proposed by Kitaev, where you have it's a one-dimensional model. You have the chemical potential term, you have the hopping term, which is just nearest neighbor hopping, and then you have something which is called a pairing term, which is also the nearest neighbor pairing. This is different from this because this does not have the dagger, right? I mean, it's not a particle which is moving from one to the other, it's just coupling the particles on two different sides. What one can do is, this particular model can always be rewritten in terms of, I can write the Cx, which is a complex fermion operator, in terms of two other operators, which I'll call gamma Ax and gamma Bx. And similarly, Cx dagger is just the Hermitian conjugate of that. And here, it's gamma Ax and gamma Bx, which are called Majorana modes. They anti-commute like fermions, right? Because they're just made up of these fermion kind of models. So they anti-commute like fermions. They're Hermitian operators, and they satisfy gamma Ax squared is equal to 1 and gamma Bx squared equal to 1, whereas fermion operators satisfy Cx squared is equal to 0. So as we already saw, the pairs of Majorana fermions, you can take any two Majorana fermions and make an ordinary fermion out of it. So what I want to now do is I'm going to look at this model in two different limits. In the first limit, I'll switch off T and delta so that I'm only left with this term. So here I have only, I take that mu to be negative and I switch off T and delta. So I only have this model. Mu is negative so that I can get a positive Hamiltonian. And then I rewrite this Cx and dagger and Cx in terms of the Majorana operators I wrote down. If I do that, what I can see is that you can think of this as just a coupling between the gamma A Majorana mode and the gamma B Majorana mode at the same site x. Right? So this is a single site x, so x is equal to 1, x is 2, x is 3, x is 4, n and so on. And this is only coupling the Majoranas at the same site, right? Because it's only having a coupling term between these two. This is just a constant term. So here, the ground state, you can get a unique ground state, and the ends of the chain, the two ends of the chain don't play any definite role. On the other hand, this same model, I can study in a different limit where I'll set t is equal to delta and mu is equal to 0. If I write the model in the other limit where t is equal to delta is non-zero and mu is 0, then the Hamiltonian can be written in terms of t. It's only this hopping term and the pairing term. And in that case, I find that I can write this entire model reduces to, in terms of the Majorana modes, to gamma bx and gamma a x plus 1. So then here the bonding is between these two and so on. And the two end Majoranas are completely left. They don't even come into the Hamiltonian. So what one can do is, of course, since any two Majoranas, one can make them into a fermion. You can pair them into a fermion. You can always make a non-local fermion from these two Majoranas. And there is a double degeneracy, since the Hamiltonian is independent of whether this fermion state is occupied or not. You know that you would get a double degeneracy of the Hamiltonian, and the ground state is doubly degenerate. But what the main point that I want to make over here is that when the model, and this I've taken some special limits, but I want to only make the point that when I write the model in terms of Majoranas, it's extremely easy to identify what are the end modes or the Majorana modes. Okay. With this background, now let me go on to say what happens in higher order topological superconductors. So here, I can't hear.
So there is a Hermitian conjugate part also.
Yeah.
So can that be ensured that the left hand end,
yeah,
there can be a B type Majorana gamma B?
If you work this out, it comes out exactly like this.
Okay. So this is
the Hermitian conjugate will not make it opposite. Is that what you're asking?
Yeah.
No.
Okay.
Along with the Hermitian conjugate, you will have to write the model fully with the Hermitian conjugate term, and this is what you will get.
Okay.
So given the way I have defined the fermion, this is all that you can get.
Okay. No, actually, I was thinking that why you are saying that there is doubly degenerate.
It's what?
Doubly degenerate.
Doubly degenerate. The double degeneracy comes from the fact that I can make a fermion out of gamma A1 plus gamma n Bn by root 2 or whatever it is, right? And this is the fermion states. F and F dagger.
Okay. Yeah.
And that state can either be occupied or not, but the Hamiltonian doesn't know anything about it.
Okay.
Right? Because it doesn't come into the Hamiltonian.
Yes.
So both of them will be, it will not make a difference to the Hamiltonian. So the ground state becomes doubly degenerate. Because of the occupation or non-occupation of that state.
Okay, right. Thank you.
Yeah, so as I said, the main point I wanted to make was that when the model is written in terms of Majoranas, it is easy to identify these things, because as we could see, very simple algebra could do that. So now let's get back to higher order topological superconductors. Here there was a nice model written in terms of Majorana mode in 2018 by Wang, Lin and Hughes, where they wrote down a model which basically has 4 Majoranas in every unit cell. So what you can do is you can write down, let's take this unit cell, and then what you can do is that you can choose your hoppings. These are all hopping terms over here. I can choose my hopping so that this gamma 2 here, it gets coupled here. So that's why the gamma 2 gets coupled to the gamma 1 of the next site. Right? This I'm going to be calling the MN site, this particular unit cell. And then the gamma 2 of this is coupled to the gamma 1 of this. The gamma 4 of this is coupled to the gamma 3 of this one, right? 4 gets coupled to 3. Then similarly, you can see that this one gets coupled to this one. So these are with n and n plus 1. And the dashed line basically means that it's a negative. I've put positive signs over here, and there's a negative sign here. And that is the dashed line that I'm sure. It's a choice that you have to make because essentially I want to put a pi flux through the cell. So it's a choice, it's a gauge choice.
And do you have charge energy on these islands or not?
Charge? No.
No charge energy.
No charge energy. This is just, the islands are just to show that it's a unit cell. And I'm putting a pi flux through essentially pi flux in each placket because of this change in sign of one of those things. And I've chosen now the hopping so that basically one Majorana mode is left out at each end.
But if you have this coupling between Majoranas of different islands,
Yeah.
don't you remove the degeneracy?
Don't you remove what?
Don't you remove the degeneracy?
The degeneracy.
I mean, you have on each island.
No, the island, it doesn't mean anything. It's just I'm choosing a model. I'm creating a model where there is a cell. I'm making a unit cell like this. I'll rewrite it in terms of fermions. But
If you take an island separate,
Yeah.
then the 4 Majoranas,
yeah,
of course, degenerate, they form 2 Dirac fermions,
Yeah.
zero energy.
yeah,
But now you take one Majorana endpoint on one island and current coupling for another Majorana
on another island.
So this current coupling,
Yeah.
means that you have essentially 2 type wires.
Yeah,
that are
so
current coupled. And
Yeah.
This does not remove the degeneracy.
yeah, this is not a degenerate model. Ultimately, I'm going to get a degeneracy only because of the 4 Majoranas. Otherwise, it's like it's a hopping model, right? It's, yeah, exactly. Yeah, I want to leave only 4 modes which are degenerate, and the removing are all. I'm removing the degeneracy.
Also these four current coupled to other.
No, these 4 are not.
Oh, the corner one.
Only corner modes. So they're going to. I'm going to be left with only 4 corner modes. All the rest of them are out of this picture. And this pi flux is needed to ensure the quantization of the quadrupole moment, which is the essential physics of higher order topological insulators or superconductors. Because if you do not have that pi flux, then you actually get edge states which are gapless. I want to gap out the edge states. So the only way to do that is to actually put a pi flux through the, yeah.
Can you use the microphone, please?
Fermion model, I mean, like, where do you start writing fermion operator and derive this?
Yeah, that is in the 1D case.
2D?
Yeah, I'm going to come to that. Just coming to that, right? Yeah. So yeah, what I want to say is that the pi flux is needed to ensure the quantization. And if you look at just the edges seem to look like the Kitaev chains that I talked about earlier. But they have one edge Majorana. If I had thought that this was a Kitaev model by itself and this was a Kitaev model by itself independent, then I would have had 2 corner Majorana modes. So here we've made Majorana corner modes by construction, and as he was already asking, there's different choices of grouping these Majoranas to make 2 complex fermions. And then one can, once I write the fermion model, I can decide how to put normal state and put delta superconducting pairing gaps and all. So the one tries to choose groupings that give gapless normal bands and then the pairing terms describing intrinsic superconducting tendency. So the model that you get just from fermionizing, putting those things in terms of this is a choice. I mean, I'm choosing one particular way of grouping those Majoranas into fermions, then I get this kind of a model. That the only parameter there was T, here also you have T, and now I have written this model in terms of 4-band model. Sigma is like a spin, tau is like a orbital spin or whatever you call it, and you find that this is exactly, one can check by writing the size in terms of Majorana modes, that this Hamiltonian is the same as the earlier one. So it actually has corner Majoranas by construction. And the interesting point is that one can show that this model has corner Majoranas even after perturbations are added, provided particle hole and some mirror symmetries in the crystal are respected. So that's what you need. So I'll leave this here. I mean, this is the background for the higher order topological superconductors. And then I wanted to briefly discuss something on flux periodicity in superconductors. And then I'll come back to our model and what we of a topological, higher order topological superconductor and what happens when you have fluxes through that. So are there any questions about this earlier? Okay. So this is something that, you know that if you have a metal ring and you have a flux through the metal ring, then the current through a thin metal ring oscillates with the periodicity of phi naught, right? Phi naught is hc by E. And that simply comes because you can write down the energy and the energy bands just get shifted. If I take n plus phi by phi naught squared, and if phi is equal to phi naught, they just get shifted. These parabolas get shifted. And you can calculate the current in this kind of a thing. And the current will always be periodic with this metal periodicity. But in a superconducting ring, the flux periodicity was seen to be hc by 2e. At a naive level, it is often said that the factor of 2e is due to Cooper pairs carrying twice the charge. But of course, that is not a very good explanation because the Cooper pairs are not tightly bound together. So it is not clear whether they traverse the ring independently or separately and so on. So you need a better argument. And this was long back by Byers and Yang and Onsager, who showed that you essentially have two classes of superconducting wave functions. You can either have a pairing of electrons with plus k and minus k momentum, right? I mean, this is the same as these parabolas. At plus k and minus k momentum, which will have a zero momentum pairing. But you can also, exactly at phi naught, at half the flux intermediate, what happens is that you can also have pairing between a state at q and a state at, if a state at k and a state at minus k plus 1, so that you get a q is equal to 1. I think this can also be seen from here, that essentially what happens is that the things get degenerate at one different value of k, right? Because you're just displacing these parabola, you can show that each of them, the degeneracy becomes at one different value of k. So what this means is that the degeneracy of the pairing of electrons like this can also lead, you can also have pairing of electrons like this. And this is what is the reason that you get this periodicity of hc by 2e, because of the fact that at that flux quanta, by hc by 2e also, the wave functions you can form pairing, because they are degenerate states which can be paired to form the Cooper pair, right? So this is the I mean, understanding of why you have Hc by 2e pairing in normal superconductors. But this simple picture is not always true, and there's been a lot of recent work which shows that S-wave superconducting rings with diameter smaller than the coherence length shows Hc by E and not Hc by 2e periodicity, because this degeneracy breaks down. And there's also work which shows that the high temperature D-wave superconducting ring shows Hc by E periodicity for some other reason which they call reconstruction of the superconducting condensate. And it's known in some sense that topological superconducting rings have Hc by E periodicity, and recently these people have given some protocol as to how this can be measured, which is why I've referred to them here. So with this thing, let me now talk about what we wanted to do. We started with a 4-band model defined, it's a variant, or in fact this was also introduced by this in the same paper by Taylor, Hughes and others, and it's a 4-band model which where in the earlier case, here sigma and tau denote operators in spin and Nambu space. The symmetries that this model has are particle hole symmetry, mirror symmetries, where by mirror symmetries I mean that if mx h k mx inverse gives you h of minus kx ky, so only the kx changes, so it's only along the x direction, or the mirror symmetry in the y direction, it only changes ky. And the mirror symmetry is anti-commute, which is why the reason we needed the pi in that thing. And you need this mirror symmetries to anti-commute because otherwise the edge states become gapless. So for Bx is equal to 0 and lambda as delta is equal to t, this reduces to the earlier model, which we already know has corner states. And what we find is that we can see that this can be shown to be topological for Bx is less than lambda.
What is Bx?
Bx is just a parameter which you can add to the, I mean, the point is you have these corners, Majoranas, then you can add various perturbations to it and the corners states still survive, and Bx is one of those. I think, so you can, it's just generalizing that model.
I think this would be the mass in the original Bernoulli Hughes Yang.
Yeah, which will change sign as this thing, yeah. In the two-dimensional normal topological insulator.
No, actually it's not dependent on position. It's the x component.
It's just, no, this is not a, yeah. You can have, yeah, the perturbation could have been Bx, By and so on, so we just choose one. So if now in this model, if I switch off delta, then this turns out to be a normal metal. Without delta, it's just a metal, right? And it corresponds to a two-dimensional Dirac metal with 4 mirror symmetric Dirac nodes. Then I'm including the pairing term. And I'm also saying that because of these mirror symmetries that are needed to generate this higher order topology, it's only possible if I choose the pairing term to be of the form Px plus Ipy. It will not work for other possible pairings such as S, D and all. You will not generate this higher order topology. Because I want it to be have that Mx and My symmetries. So now with this I can compute the spectrum of the model, and spectrum as a function of this parameter Bx. And what you see is that as long as Bx by lambda is less than 1, we get actually 0 energy states. And if you plot it, you find that you get 4 corner modes, and these are these 4 states. These are the only 4 states which are there at 0 energy. Other states are all massive. So for this, we get a second order topological TSC2 superconductor with 4 corner states. now what we do is we introduce a solenoid at the origin of the 2D sample so that any closed loop enclosing the origin encloses a flux phi. So this is like the metal ring or something like that, but the simplest way we've done it is just by introducing a single vortex. If we set delta is equal to 0, that is we turn off the superconductivity, then we can show that the spectrum shows the standard periodicity with respect to, it gets repeated. These are just some of the 3 states that we've plotted. And you see that phi by phi naught, our phi naught is always hc by E, it's periodic in that.
So why do you have several curves? Why do you have several curves?
I've just plotted 3 different energy eigenstates. More than 3, several eigenstates.
These are different what?
Eigenstates. Right. This is just from the spectrum, I'm just plotting different eigenstates. Right? So I'm just showing that the periodicity is there as a.
The spectrum is indeed periodic on the one.
Yeah.
But if I follow one particular level,
Yeah.
then this level has a larger periodicity.
No, I think this is just one level, this is another level. They are independent levels that are being plotted.
But that's exactly the point you make too.
But this doesn't even have there's no superconductivity, it's just a metal. It's a metal ring.
Nevertheless.
Yeah, so, yeah, right? So I think it's just a metal ring, this thing for.
This is just crossings of energy levels, right?
Crossing of.
Happens with the parabolas.
Yeah.
There are other
Let's
cases.
have one person at once talking.
There are other cases
Yeah.
that.
Yeah, it's okay to wait. Yeah, it's okay. This is fine. I'll think about this and we'll maybe discuss it later. The point is that what we wanted to say is that once I put in a delta, then a constant delta is not even qualitatively correct once I include a vortex. So we actually try to solve for delta self-consistently. Okay? So you need to find the self-consistent delta by solving the BDG equations in the presence of the vortex self-consistently. And close to phi is equal to phi naught by 2, we find 2 self-consistent solutions, which is kind of reminiscent of this is the one without a vortex. Once we introduce a vortex, we of course, and we have a non-zero delta. This is without delta. Here, once I've introduced a delta and a vortex, besides the 0 modes, we also find that close to phi naught by 2, there are 2 self-consistent solutions which seem to be coming up. And this we thought is somehow, this is just the plot of the 3 lowest self-consistent energy eigenvalues for delta 0 and delta. This is delta 0 and delta non-zero. So as I said, besides the 0 energy states, there are also 2 self-consistent places close to phi is equal to phi naught by 2. And then we can also plot the total energy of all the states as a function of phi by phi naught. And what we find is that close to phi by phi naught by 2, there's these 2 states, there's very close, it almost becomes degenerate at this point. This is for the case after delta Vx is equal to 1.5, where there's no superconductivity. Superconductivity has disappeared.
What are the 2 states where are the 2, are there different colors or different plots?
No, they're not 2 states. The 2 self-consistent solutions, we follow the lower energy of the 2 self-consistent solutions. One has a higher energy, one has a lower energy. But self-consistency will automatically take care of the change in the momentum. Yeah, maybe that's why people don't do it for we were wondering, it hasn't been done for the usual P plus IP superconductors. Self-consistency nobody works with. I see. And then we also computed the total circulating current. And you can again see that for Bx by lambda is 0 and where there is where you've set the Bx to 0 and at 0.7, right? And here you again see that there is this change in periodicity which is happening, meaning it's not exactly periodic in phi by phi naught, but it's getting these extra peaks. It's strictly periodic, of course, only in phi naught, but it's roughly periodic in pi naught by 2. That's what I wanted to say. So what we wanted to understand was, why does this periodicity change? If I plot the self-consistent spectrum in the absence of any vortex and just using the self-consistency, what you see is that it shows a crossover from a topological superconductor to a normal superconductor, roughly around 0.6. The point, because you have these zero modes which exist up to the value of Bx by lambda is 0.6. If you took a constant delta, Bx by lambda is 1, is where it changed from being a superconductor to a normal metal. But here you find that roughly around 0.6, the zero modes mix with the higher energy modes. So you are no longer in a topological superconductor regime. So we say it's a crossover from a topological superconductor to a normal superconductor, because if you plot delta, the self-consistent delta, then that actually becomes 0 only at 1. So there's a region between 0.6 and 1 where it looks like it is a superconductor, but it's not a topological superconductor. So topological superconductivity only survives till this because of the mixing of zero energy levels with higher energy levels. So what we are saying is that the topological superconductor with a phi naught periodicity transitions to a normal superconductor with phi naught by 2 periodicity, and then to a metal with phi naught periodicity. And usually people say that experiments of these kinds cannot be done because both topological superconductors and normal metals have phi naught periodicity. So you don't know whether you're just seeing the Aharonov-Bohm periodicity or you're seeing this periodicity due to the superconductor. But now what we're saying is that there is a region in the middle where it's separated by a phi naught by 2 periodicity. So this is the main point that we wanted to say. I guess this is the this thing is the main issue that we have, that we get this doubly degenerate, we get two self-consistent solutions, one of which is higher in energy and one of which is lower in energy. So we need to always follow the one which is lower in energy. And now finally we also did the calculation of trying to see how we can tune the transitions. If we can tune between these phases, then the change of the periodicity of the circulating current can be measured. And since you need to change parameters in the Hamiltonian, one way of doing it is always to couple it to light and do Floquet. So we can shine elliptically polarized light and obtain in the high frequency limit, we can obtain an effective static Hamiltonian by expanding in powers of 1 over omega. And then if we do a computation to order 1 by omega squared, it shows that Bx can be tuned, in fact, by having light. So by shining light, we can change the periodicity of the circulating current. Okay, so that's the main point that I wanted to say. What we've done is studied Majorana modes in a model of a higher order topological superconductor. We've introduced a vortex at the origin in a higher order topological superconductor. And the periodicity of the energy levels and circulating current changes from phi naught to phi naught by 2 as the superconductor transitions to a normal superconductor. And this change in periodicity can be tuned by coupling to light. Thank you.